In this problem, we're given two semi-infinite planes. One is the phi equals 0 surface, the other is the phi equals pi over 2 surface, but there's a small gap between them to keep them electrically isolated. 100 volts is applied as shown, so the phi equals pi over 2 plate will charge up positively and the phi equals 0 plate negatively. I've drawn some of the charges, and notice the way I've drawn them is the charge density is decreasing the further I get from the origin, the larger the value of rho. This decreasing charge density with increasing rho should make sense to you from your mental models of the relationship between charge density and electric field intensity and the relationship between potential and the integral of the electric field intensity. The potential difference between the two plates is equal to minus the integral from the phi equals 0 plate to the phi equals pi over 2 plate of E dot dl. This potential difference will be independent of your path of integration between the phi equals 0 and phi equals pi over 2 plates. Consider the integration when your path is along a constant value of rho. For a small rho, you're traversing a much smaller path length than for a large value of rho. So the electric field intensity has to decrease as rho increases, so you get the same potential drop. And since decreasing charge density leads to decreasing electric field intensities, that's why the charge density decreases as rho increases. Since our two conductors are surfaces in the cylindrical coordinate system, the phi equals 0 surface and the phi equals pi over 2 surface, the potential field and electric field intensities will have cylindrical symmetry, so will work in cylindrical coordinates. The two conductors are infinite in the z direction, which is out of the plane of the page, so the potential will not depend on z. I've drawn some additional phi surfaces. This one is at pi over 4 radians. So if you were integrating E dot dl with a constant rho, when you get to this pi over 4 plane, you're halfway through your integral. So this plane is going to be at 50 volts. So the pi over 4 plane is an equipotential surface at 50 volts. A similar argument could be made for any phi plane, so the potential will not vary with rho because phi planes are equipotential surfaces. To find the fields, we're going to have to use Poisson's equation. Here we have Poisson's equation. Let's assume everywhere is free space, so we'll use the permittivity of free space. Where we will apply Poisson's equation is in the free space region where there is no charge, the charge residing on the conductors. So the Laplacian of V in the free space region is equal to 0. For our second order differential equation, we'll need two boundary conditions. One is the phi equals 0 conductor at 0 volts, and the other one is the phi equals pi over 2 conductor at 100 volts. Let's now write the Laplacian of the potential in cylindrical coordinates. Here is the form of the Laplacian, and since the potential only varies with phi, the partial with respect to rho is 0 and the partial with respect to z is 0. So this term is equal to 0. We can multiply both sides by rho squared and get the second derivative of v with respect to phi. Integrate once, we get the partial of v with respect to phi equals a constant a, and integrate again, we get v of phi equals a phi plus b, a second constant. We can find the constants a and b with our two boundary conditions. So when phi is 0, the voltage is 0, and we see that b must be 0. So now we'll put in our second boundary condition to find a. So we can solve for a, and we see that a is equal to 200 over pi volts. So our potential field is V is equal to 200 over pi times phi volts. So we found our potential field, and we can find our electric field intensity now from E is equal to minus the gradient of the potential field. Here is the equation for taking minus the gradient of the potential in cylindrical coordinates. Since V only depends on phi, the partial of V with respect to rho is 0, and the partial of V with respect to Z is 0. So for V, we substitute in 200 over pi times phi. Taking that partial with respect to phi, we'll get 200 over pi volts. And with rho and meters, that will end up giving us units of volts per meter. So here is our electric field intensity. And just to remind you, this is the free space region in the first quadrant for our potential field and our electric field intensity. So our electric field intensity lines are given by this equation, and our electrical potential field by this equation. It turns out we are not quite done. The potential difference between the plates is given by minus the integral of E dot dl from the phi equals 0 to the phi equal pi over 2 plate. This result is independent of the path. We could equally well take a path through the fourth, third, and second quadrants. So there's actually an electric field and a potential field in these second, third, and fourth quadrants. There will be positive charge on the left side of the phi equals pi over 2 plate and negative charge on the bottom side of the phi equal 0 plate. And the electric field going from the positive charges to the negative charges. Now, because we have to get the same voltage drop and we're traversing a much greater distance, the electric field intensity will be weaker in the second, third, and fourth quadrants than it was in the first quadrant. The form of our Poisson equation will be the same, but now we're going to apply it for phi going from pi over 2 to 2 pi, and our boundary conditions will be that the potential at pi over 2 is 100 volts, and the potential at 2 pi is 0 volts. When we take the Laplacian in cylindrical coordinates, we'll have the same form for our differential equation. So the form of the solution again is the potential equals some constant times phi plus a second constant b. And now we will apply our two boundary conditions. So at phi equals 2 pi, the potential is 0, and it's equal to a times 2 pi plus b. So b is equal to minus 2 pi a. So we replace b with minus 2 pi a, and now let's apply our last boundary condition at phi equal pi over 2. And we apply the boundary condition, and we can solve for a. A is minus 200 over 3 pi volts, and substituting for a, we'll get our potential field. We can now find the electric field intensity in the second, third, and fourth quadrants by taking minus the gradient of the potential field. And that works out to be 1 over rho times 200 over 3 pi in the phi direction volts per meter. We were also asked to find the charge density on the plate at phi equals 0. In the next video, I will show how to do that, but the problem will have a different potential across the plates, so the electric field intensity will be 1 over rho times 108 pi instead of 1 over rho times 200 over pi.